Hello, everyone. It's such a pleasure to talk to you all today. I hope you're having an excellent conference so far. My name is Jo Franchetti, and I am a developer advocate at Ably. And Ably is a pub/sub messaging platform, or you might hear it be called a real-time messaging broker. And what it does is it allows developers like you to build reliable, scalable apps with real-time data. And we're going to talk today about building apps with pub/sub messaging and specifically how to build a multiplayer game with Vue.js and real-time elements. But before we dive into the tech, how are you all doing? I hope you're all well and you're all coping with lockdown and social distancing and, a global pandemic. Because it's been tough. It's been super tough, to be honest. And not being able to see friends and family as easily as we used to. We've all gotten used to these weird remote ways of working. And one of the ways that I've been trying to keep in contact with my friends during lockdown is playing online multiplayer games. And I used to host a weekly board game night back in the before times when we were allowed to see each other in person. And I miss those a lot. And I've been trying out replacements like Tabletop Simulator and Jackbox to try and get the same experience. But I kept running into these snags. In order to play Tabletop Simulator, my friends all had to go through the process of signing up for a Steam account and downloading and installing the game. And sometimes these steps are enough to make them just give up entirely. And then I tried playing Jackbox, but in order to do that, we had to have one person streaming their session over video chat so that everyone else could play remotely, which took technical skills and time. And often my friends were just like, oh, can we not? Can we just chat? I'm bored of these steps already. And that wasn't the experience that you want when you're trying to hang out with your friends. I wanted something that gave a similar experience to all of us sat around a table playing a board game with minimum setup, very low learning curve, and maximum laughs. So I wanted to build a game that people could pick up quickly and play without needing to install anything or sign up for anything. And well, everyone has a web browser. And these days, web browsers are incredibly capable and feature-packed, so why not build a game that runs in the browser? So what did I decide to build? Well, I wanted something with a simple set of rules that I can describe in code, something that my friends will pick up easily, that can have a nice, simple UI. And the brilliant thing is that most board games are, by design, a set of rules and systems that move players through the game. And turn-based games like Pictionary or Scrabble or Noughts and Crosses or what you call tic-tac-toe in the States are not only easy to learn, but they're also easy to describe. We can write down the rules of the game as a series of logical steps. And a board game, its component pieces, so its rules, its outcomes, they're all just a system. And all computer games really are is a set of rules which are captured in code that apply to some state. And the nice thing about board games, especially the simpler games like Pictionary and Scrabble, is that you can see how the state transitions, the way the game mutates the data as the turns happen. When somebody passes a card to another player, that's an event. When somebody puts a tile on the board in Scrabble, they're mutating the state of the board physically. And the nice thing about party games especially is that they rely on the game state, so the set of rules that describe how the game plays, being maintained in the players' heads, so the logic needs to be very simple and straightforward. And this makes them really nice to model as systems because there aren't too many rules that you need to encode. And board games are a fun example of a computer science concept called state management, which is basically how information flows through a system. And one of my favorite party games is called Eat Poop You Cat, which is like a cross between Pictionary and telephone, and it requires just a pen and paper and 4 or more players. So let's say we have 4 players. So we've got player 1, 2, 3, and 4. Each player is given a prompt to draw from, much like in Pictionary, but for simplicity's sake, what I'm going to do here is illustrate a single round just for player one. So player one is given a prompt. So in this case, the prompt is abducted by a butterfly, and they have to draw something on their card that represents what the prompt says. Once they've done that drawing, they pass it on to player two, who has to write down a phrase which describes what they can see. Once they've written that down, they pass that phrase on to player three, who draws something based on that phrase. They then pass their drawing on to player four, who will write down a phrase that explains what they can see in the drawing. If there are more than 4 players, then the game will continue on like this, swapping phases of drawing and writing until we reach the final player. We then reveal the stack to all the players and laugh about how ridiculously the original prompt has transmuted and how terrible or brilliant we all are at drawing. So this is the game that we're going to build today. And if we were to write out the rules of the game, they'd look something like this. And if we take a look at these rules here, we can start to reason about how we might split them up into state and events that change that state. So every time there's an event that changes the state, we call it a new game phase. And these first 3 steps here, where we're creating the game and waiting for our friends to join the game, that is the setup phase. And then we move on to the next game phase, where the host will click a button to start the game, and we're in what I'm calling the dealing phase, where each player gets a card with a prompt on it. We then will start a timer for 180 seconds to draw something. It might sound like a short time, but it's actually pretty long. And this means that they can submit their finished drawing before the time is up if they need to, but the round won't move on until either everyone has submitted their picture or the time is up. We'll then collect in the drawings and pass them on to each player, and each player will then be given 180 seconds to write a caption. Again, they can't submit their finished, they can submit their finished drawing before the time is up, but the round won't move on until either all of them have submitted or the time has run out. Now, the reason why we're applying this timer is otherwise it would be possible for a player to maybe get up and go and make themselves a cup of tea or disappear entirely, take a phone call, whatever, and pause the game for everybody indefinitely. So we run a timer to make sure that the game doesn't get stopped by one player disappearing for whatever reason. So once the captions have been written, we collect the captions and we pass them on. And this repeats until each player gets their original stack back. We then will reveal the stacks to each of the players and ask them to vote for their favorites. And we collect the votes in and we can show who won. So we've now converted the things that the players will do physically into state and events. And to capture this as code, we need somewhere where we're going to store that state. And we need some code to execute every time one of the game events causes the state to change as the game progresses. So what we're going to build is a state machine, which is going to execute the game. And then what we're going to need to do is build a way to share that state between multiple machines, so that all of the players will keep up to date as the game progresses. And in traditional multiplayer games, this could all be handled by a game server of some kind. But all we really have now is a browser. So the question emerges, can we build the kind of game that would normally require a server to maintain some state somewhere using only client-side code? And the answer is yes, we can, using something called peer-to-peer networking. So peer-to-peer, and you might see it written as P2P, the number 2, refers to a network of computers and or other devices that share and exchange data or workloads. And in terms of our game, these computers or peers would send messages to each other in order to control the game state. And this differs from a client-server architecture where one central machine controls the whole game. And the great thing about peer-to-peer is we don't need a central server to manage the game, but will still need a host. And this is the computer that is going to create the initial game for all of the peers to join. And whenever the game host accepts a new client to the game, it has to also notify all the existing clients that this new player has joined so that they can all ensure that they connect to the new player too. And a good number of games use peer-to-peer networking, including a lot of strategy games, a lot of sports games, some driving games. And conversely, client-server architecture is used for your more MMO-type games, first-person shooters, that kind of thing. So why might we want to use peer-to-peer? As we mentioned, it's quite simple, and it's a nice, effective way to manage communication between a small number of computers. We're not reliant on a central server, which means that we don't have to pay to host a central server anywhere, nor do we need to worry about maintenance or uptime or reliability. However, there are some points which we should consider. We're building here a game where the players won't be able to join and leave mid-game. If they leave mid-game, then suddenly we're missing a player and the whole round doesn't make any sense. And this sort of drop-in, drop-out approach is much more complex to implement in P2P, as we need to manage that in a state machine. And for example, what happens if the host drops out? We need to find a way to pass the host token to somebody else. And for more complicated games, it's difficult to ensure that the game is completely deterministic so that each round plays out identically on each machine. And if one small change happens on one machine, it's kind of like a butterfly flapping its wings and causing a hurricane on the other side of the world. One tiny difference results in increasing desynchronization of the machines over time. And the next limitation is that in order to ensure that the game plays out identically on all the machines, we need to wait for all of the players to join in some kind of waiting room, lobby, that kind of thing. And we need to make sure that all of the players' turns are received before we simulate moving on to the next turn. And this means that, unfortunately, each player in the game has latency which is equal to the slowest computer or the most laggy internet connection, which, to be honest, doesn't really matter for this kind of turn-based game, but it certainly wouldn't work for a first-person shooter. And mostly peer-to-peer games will hide this sort of slow loading time or low latency by providing some sort of audio feedback immediately or playing a cosmetic animation. And as I mentioned earlier, we're going to have a 180-second timer so that players can't delay the game. And what we can do while, for example, if a player submits their drawing before the 180 seconds is up, we can play a nice little waiting animation just to tell the player that the game hasn't crashed, it's still going, we're just waiting on other players. And the final limitation occurs because of the way the game synchronizes by sending command messages which change the state. In order for this to work, as I mentioned earlier, it's necessary for all of the players to start at the same initial state. So we're going to need some kind of lobby where they wait before we commence the game. And again, for this depicted game that we're building, this isn't really an issue. Players are all going to join at the same time and finish at the same time. We're not going to have people dropping in and dropping out. And so it might sound a little bit like peer-to-peer has a lot of cons rather than pros, but for this particular use, for this particular game that we're building, with a very minimal amount of state and gameplay that won't be changed by low latency machines, it's a really good fit. So when you build a peer-to-peer engine, all the clients need to know the state of the game, and they are all required to stay in sync for the duration of the game. And we've already abstracted the game into a series of phases, for example, deal, draw, collect. And all that is needed to network this together is to run exactly the same set of commands and turns on each player's machine, starting from an initial state. which means that we need a way for the browsers to communicate with each other as and when the state changes in real time. And the way that real-time communication is managed by browsers usually is with WebSockets. And this is the protocol which allows real-time communication on the web. And WebSockets allow us to open a connection for communication between two devices. So we open a connection, we do a little security handshake, and then we're able to send binary data between the computers. And the brilliant thing is that the connection stays open, unlike an HTTP request. So communication can actually happen in real time. We don't have to keep polling for changes like we would with a REST endpoint. But, and there is a but, WebSockets come with a whole bunch of extra configuration and architectural decisions. So for example, what happens if the host drops out or somebody loses connection? How can we let that user reconnect? And how do we store and resend the messages that they missed while they were out? How do we ensure that the messages that we're sending arrive in the correct order? And what happens if we have multiple games being played at once? How do we separate out the different bits of data on different communication channels? And usually, instead of doing all of this extra engineering ourselves, we would use a library or a service to do this. And there are a lot of different options out there, but I work at Ably, and therefore I have the entire of the Ably ecosystem at my disposal. So I use their service, and obviously I think it's pretty great. They're a service built on top of WebSockets, which comes with all of the things that I just mentioned out of the box. Ably uses something called the PubSub pattern to send messages between machines. And PubSub just stands for publish and subscribe, where we use channels for message exchange, and users can publish messages on those channels, so they're sending messages out. And then the peers can subscribe to that channel to receive the messages that they sent. And Ably is the message broker, which is sending the messages. And the data that's sent in those messages is basically just binary data, so we can send whatever we want. And because we're building in the web, we are going to send JSON. And we can create a JSON structure for each phase of the game. Each phase is going to have a message type, which indicates which phase we're in, and a payload, which is the data that actually needs to be shared. And by sending and receiving these messages, we can keep each peer in sync and progress the game. So let's say, for example, we want to send a message when a player has submitted a caption. First, we're going to create a channel with a unique name for each game. Then we can connect to that channel using Ably's get method. And once we're connected, we can start to publish our JSON data. And other players can subscribe and action that data when it arrives. And this is the foundation of the architecture, which will work for a simple game like the one we're building today. And this is the service which lets us manage the state across multiple machines. So we have an architecture, we have a way of managing state. Now we need to decide what we're going to build the game in. And we're in a browser, so of course we're using HTML and CSS and JavaScript, but could a framework help us out here? Well, I decided to build the game with Vue.js. I'd used it before in some other smaller projects, and I really enjoyed it. It's got really approachable documentation and resources, and they really lower the barrier to entry. And there isn't really a huge burden of learning with comparison to its contemporaries, I have to say. And I didn't want the overheads of some of the other frameworks, like a bigger payload or complex build tools or build steps. And the fact that you could just use Vue with a single include, I think is brilliant. And you can use Vue with plain old HTML to create the Vue components, which is much simpler than JSX, for this fairly simple implementation of a game. If you've not seen Vue before, here's an abridged sample of some Vue code. So what we're doing here is we're finding an element with the ID of app in the markup, And we will treat any elements within the markup inside this app element as things that can contain Vue directives. So these are extra attributes which are going to bind data and manipulate the HTML based on the application's state. And the Vue app makes the properties of the data object available to bind into your markup, such as in this example here, the greeting. And when the data changes, it'll re-render the parts of the UI that are bound to it. And Vue exposes a whole load of useful methods which can be used to implement things like click handlers and callbacks from the UI, like the do something function in this example. And the corresponding HTML would look like this. So here you can see Vue's v-if directive, which means that the div and its contents will only display if the display greeting data property is true. And you can also see Vue's binding syntax here, where we use bracket bracket greeting to bind data to the UI. And Vue makes it super easy to create data-driven components with just plain old HTML. So what I did was I created a separate component for each phase of the game, and then I used logic to display the correct one as the game progresses. So let's take a look at some of the components. So here we've got a component for a host to create a game, and one that shows the players that have joined, so this sort of lobby idea. We have one for drawing here, so we have a blank card with a bunch of different colors underneath and a timer bar which is going down the side, which also shows the caption. And then we have one for collecting captions as well, which is just a little text input where users can type. So let's talk about how the game is actually built. The Vue app is in the root of our /app directory, which will deal with our main user interactions. And then the game is defined as a set of cards and handlers along with the state machine. And the P2P directory that you can see here contains all of the message sending and handling code that the game needs. And then we have the Vue components themselves. So to capture the logic of the game, we need to break the game phases into different handlers that represent both the logic of that portion of the game and the logic that handles user input during that specific game phase. And this idea is kind of part state machine, part command pattern handler. So here we're creating a game state machine that takes a game definition, which is comprised of the steps that we spoke about earlier and an optional context object. And it manages which steps are executed and when. And it will always expect a game to have a start handler and an end handler. And it will use those strings to know which game steps we start and end on. And the constructor for the game state machine takes these steps and the context and saves them within itself. So what the game state machine is going to do is it's going to keep track of the current step key. This is whatever string we use to define the names of the steps within the game. It's going to keep track of time. It's going to await the execute function of the start handler, and it's going to evaluate the response that it gets. And once a response from the current handler has been received, if the current step key is end handler, then we return because the game is concluded. Otherwise, we're going to update the current step key to be the target of the transition to response, which will change the current active state of the game. So we're going through each step. Then we're going to call run again to process the step that we've just arrived at. And this flow of moving between game steps based on the outcome of the current step allows us to define all kinds of games, not just the one that we're building here. So our game logic is going to be encoded as a series of handlers, which are configured in our state machine. And each handler is going to represent a single phase of the game, like dealing the cards or asking for users to send drawings, etc., etc. So this is what the entry point of the depicted game looks like. It references all of the game handlers and returns the game definition needed to create a game. And it's a function. We're going to pass an Ably connection inside the handler context parameter, and it returns a fully created game state machine instance to run in the Vue.js app. And as I mentioned earlier, the game is defined as a series of named handlers. So we have our start handler, our deal handler, our get user drawing handler. And each of these handlers are imported from the depicted.handlers.js file, which we saw when we looked at the architecture earlier. And each handler has access to an Ably channel. And the browser of the hosting player keeps track of where all the game hands are, what the state is at that particular point. The host then publishes messages, which all of the other clients in the game will subscribe to, and the client code in their browsers will prompt the players for input. And these handlers are interesting because they run some logic, but they also collect input from other players. So when we connect to the game using Ably, the messages that arrive over the channels are going to get routed to the active handler for the current game phase and passed to the handle input function. And these handlers are the backbone of modeling our whole game. And if you want to know how the game actually works, here's what each of our handlers does. So we have a start and end handler. Then we have get user drawing and get user caption, which both collect an input. We have the pass stacks around, which decides where we are in the game, and eventually it'll transition us to the end of the game. So the start handler is going to create a prompt deck imported from our depicted.cards.js file. It'll shuffle the deck and it'll transition to the deal handler. And deal handler is going to create a game stack for each player. It's going to add a prompt to the top of the game stack, and it'll transition us to get user drawing handler, which will then send a drawing request to each player. It will the request will contain a prompt from that player's game stack. It's going to wait 180 seconds or wait until the players have responded, and it'll transition to pass stacks around handler. We're then going to get user caption handler, which is going to do basically the same thing that request drawing did, but with a text instead of a drawing. We will then pass the stacks around again until we get to the end of the game, at which point we will get user scores. We will send a pick one request for each game stack that waits for all of the users to submit a score. And then we will run the end handler, which is going to show those scores and finish the game. And the interesting thing about the way these handlers work is we're using an async await pattern and an unresolved JavaScript promise, which is going to pause the execution of the game while we wait for user input. And this makes it possible to represent the game's control flow linearly while we wait for messages to arrive over our Ably channel. So this unresolved promise that we've got here basically pauses the code until it returns true. So say we're waiting on all of the players to finish drawing. We know we need, for example, 4 total inputs before we can move on to the next game phase. The promise that we have written here will not return true until all of the drawings have been submitted. And while we're in this paused situation, messages sent via the Ably channel will be passed to the handle input function. And this input handler will increment this.submitted each time it receives a message from Ably. And we will then run a wait until condition, which will check if the current value of this.submitted is equal to the number of players. We know that when the number of submitted drawings is equal to the total number of players, then each player is sent an image and the game can continue. The promise will resolve and the game will move on. And each step of the game has its own logic, and I'm not going to walk through each of them here, or we would be here all night. But all of the code is on GitHub, so you can have a look at yourself, and I will share the links at the end of this talk. So we've touched on how our game state machine handles the state, how it gets input over P2P messages from our clients, and how it moves between different game states. But this would be totally academic if we didn't put it together into some kind of app. So let's talk about our Vue app and its components. So I wanted the game to be mobile first, so that my friends could play on their phones or their tablets. So I had to make sure that we have enough space for users to draw with their fingers. So it had to also have touch support. And I wanted it to be as clear and obvious as possible to play, similar to how you would with a pen and paper if you were playing in the real world. So the game phases map pretty nicely into separate components, which are then implemented as Vue components. And you can see the names of the different components here. So just to briefly illustrate, we have here the create game form where the user can create a new game. And we have the drawable canvas with a timer bar and a color palette here and a drawing prompt. And the top level UI has instances of a class called P2P client and P2P server, which are stored as Vue reactive data properties, which is going to make them observable. When the P2P client receives some state transition messages from the peer who is acting as the host, it will update an instance variable called last message. And the UI interactions are bound to this last message property, and the components will only display when the state transition message they are meant to respond to is the one that has happened in last message. And what this means is that when the last message we receive has a kind, for example, of instruction and a type of drawing request, the Vue if directive on the playfield drawing component will return true and the playfield drawing component will be rendered. And this approach of only displaying whatever the last message asked for made it really nice and easy to build a UI that responded to the different game events without a lot of complicated display logic. And we wired this all up in the markup by always including each of the playfield components, one for each of the game states. And then we bind the state object to them along with the P2P client so that these components can be entirely self-contained and respond to the different game phases. And the components themselves, all they need to do is decide whether or not to display. So while I made a bunch of smaller Vue components for tiny pieces of interaction, things like copyable text box for shareable links and the timer bar component to display countdown timers, the most interesting component is the drawable canvas component. And this was a combination of two things. So I used an NPM package called Snake Canvas that I originally built for a digital whiteboard project, which allows us to track users' cursor movements and turn them into a drawing, and a Vue component that consumed this NPM package and added some methods and an event that could be raised whenever somebody finishes their drawing. And the way the Snake Canvas package works is it takes any old canvas element and it wires up all the click handlers for drawing on it with both a mouse and with touch input. And it's got some utility functions like adding the palette, which will wire up click events to an HTML element so that you can change the color of the cursor that you're drawing with. And it allows us to set things like background color or a specific data attribute on the canvas if we so need. So to use it in Vue, we just added it into the template with a div and a generated ID. We create a new instance of this drawable canvas element, and the library does all the hard work for us, adding all the handlers that we need to the element itself. And what we do when the user has finished drawing, they then click a I'm finished button, which is wired up to an emit event. And we subscribe to this event in our drawing component. We encode the data from their canvas that they've drawn as a base64 string by just calling toString on the canvas element. And we send that string as the body of the emitted event. This means that we can easily send raw PNG data once the user had finished drawing. But then we also need to be able to save the images so that we can show them to the other players. And sending images over peer-to-peer is not optimal. Images are actually quite big. Even though these particular images are small, they're still not small enough to fit inside a single message. And I tried a couple of times to compress the images down to be small enough to send in a message. It turns out PNG is actually already very compressed. So it became clear that the images needed to be stored in a system that was designed for this kind of data. And so I decided to use the Azure Blob Storage because I was already planning on hosting the game on Azure Static Web Apps. So Azure Blob Storage seemed like a sensible option to go with. It's got a really nice API that is usable in the browser so that clients can post an image as a string of data, and it'll return you back a URL for the newly stored image. So that URL is then what I send in the messages to the other players so that they can vote on the drawings in the scoring round. And the scoring round is cool because it's just built on top of all the other pieces. So I had already built a component which would display the cards when we asked for the captions, and the state machine already had the capability to wait for user input. So all I needed to do was make it possible to move the game along if the players are being too slow on voting. So what I did is I give the host a finish voting button, just in case somebody's messing around. And so what we do here is we show each user the whole stack of cards. We allow them to click on one to vote. And we send a message for each click and tally them up to show who won at the end. And that's it. That is how you build a multiplayer game in Vue.js with pub/sub messaging and with peer-to-peer architecture. And if you'd like to build your own, you can find all of the code for this game at github.com/ablylabs/depictit. It's all fully open source. Please take it, make it your own. Please add some more cards in. So we have the depicted cards file, which has all the prompts. And I'm told by my friends who are playing this regularly that they're bored and they want new prompts. So please add in some new prompts. I'm always open to PRs for game improvements too. And if you do make your own version of the game, please share it with me at This Is Joe Frank on Twitter, because I would really love to see it. And thank you so much for listening. If you'd like to have a go playing the game, you can do so at depictit.ably.dev. I have been Joe Franchetti. You can find me at This Is Joe Frank on Twitter, and you can find Ably at Ably Realtime. And of course, we are hiring. Ably has just closed its second round of funding and we're growing really rapidly. We have an awful lot of open roles. So if you'd like to come and work with me, or if you'd like to know more, you can go to ably.com/careers. Thank you so much. I hope you enjoy the rest of the conference.